Thanks for appreciating my Thevenin theorem simulation in Multisim video. After that, I received some comments that how to cross-check this theorem practically and what is application of Thevenin theorem. Now, in this video, I will try to solve this query. These are basic questions when we started practically cross-check Thevenin theorem or any theorem. First, how to cross-check practical circuit? That means in breadboard, if reading is 2.5 volt, is it correct value? Second, why 1 farad capacitor, 1 ohm resistor, 1 Henry inductor component is not available in laboratory? Third question, how to compare theoretical and practical values? And last but very important question, real world where this theorem is applicable. This is basic procedure to find Thevenin voltage and resistance or impedance in circuit. First, select circuit from standard reference book. Second, calculate theoretical values for Thevenin voltage Vth and Thevenin resistance Rth. Simulate selected circuit on Multisim or similar software to find Vth and Rth. Mount same circuit on breadboard and measure Thevenin voltage and current. Compare all results. Most of the time, students get confused why 1 ohm resistor, 1 farad capacitor and 1 Henry inductor is not available in laboratory. Rather, 1K, 10K, 330 ohm, etc. resistor, then 0.01 microfarad, 0.001 microfarad capacitor and 37 millihenry, 47 millihenry, such values available for component. When students are using reference books for numerical, they observing these values. Those are 1 ohm, 1 farad, 1 Henry. So main question, what we are studying is right or wrong. Always remember, for simplified calculation, reference books are using normalized circuit. Normalized circuit means converting real values, example 0.047 microfarad, 10 kilo ohm, 10 millihenry into normalized value. It's done by impedance scaling or frequency scaling. In my next video, I will give you introduction about these methods. Normalized circuits are good for ideal circuit analysis, but those element values are unrealistic and not practical. So, to start practically, cross-check Thevenin theorem, select circuit with real values. Before starting practically cross-check Thevenin theorem, what is the statement for Thevenin theorem? So, the statement is any linear active bilateral network can be replaced by an equivalent circuit consisting of a voltage source in series Vth with a resistance Rth. This theorem is also applicable for AC circuit. AC circuits have equivalent Thevenin impedance and always consider operating frequency is a constant for all theoretical and practical calculation. So this is a major change for AC circuit. For DC circuit, frequency is not applicable. This circuit shows a voltage source here, then R1 resistor, R2 resistor and R3 resistor. According to Thevenin statement, we are interested to find Vth and equivalent resistance for this entire circuit. So this is my equivalent circuit. This is my Rth and this is Vth. So Vth is nothing but, if I open this terminal, the current flowing from R1 and R2. So Vth is nothing but voltage across R2 resistor, and if we short this even to find equivalent resistance, then R1 and R2 parallel. So Rth is equal to R1 parallel R2 and this R3 is in series. And these are my terminal A and B. So this is Vth, this is Rth, and this circuit is Thevenin equivalent circuit. This is a problem statement to find Thevenin voltage and Thevenin resistance. Problem statement is simplify the following circuit and calculate the value of a load current IL. Here my point A and B, and this is my load resistor. RL is equal to 1 kilo ohm. If you observe 330 ohm, 330 ohm, 330 ohm, 1 kilo ohm is available in lab. So we can implement this circuit on breadboard, simulate this circuit in Multisim, also perform theoretical calculation and practical calculation. So let's start to solve this numerical. Problem statement we already know. These are the steps. First step, open the circuit. Second step, find Vth. Third step, find Rth. First step, open the circuit. So this is A point and this is B point. So at both circuit we remove load resistor. Step 1 is completed. In step 2, as circuit is open, current will flow from R1 and R2. So this is my current direction. And current will not pass through the resistance R3. Resistance R1 and R2 both are in series. Resistance R1 and R2 are in series. We know the formula already known. Voltage is equal to IR. So current is equal to V divided by R. For this loop, voltage source is a 20 volt. Then R1 330 ohm, R2 330 ohm. Answer is 0.03 ampere. To find Vth, if this is an open circuit, then Vth is nothing but the voltage across R2. Voltage is equal to resistance into current. So resistance is 330 ohm. Current we already calculated, loop current 0.03 ampere. It is approximately 9.99, or if we round up the value, it is a 10 volt. Third step, find RTh. To find RTh, we have to remove voltage source. To remove voltage source, we just have to short the circuit. Then 330 ohm in parallel. So R1 and R2 in parallel and R3 in series. And your answer is 495 ohm. Now last step. This is your resultant circuit, Vth, then Rth, and here you connected your load resistor, RL 1 kilo ohm. Again, loop current is nothing but your load current. So IL is equal to Vth divided by Rth plus RL. Rth and RL both are in series. Putting the values in formula, Vth is 10 volt, Rth 495 ohm, RL 1 kilo ohm. Your answer is 6.68 milliampere. We can cross-check the answer using Multisim. DMM is showing same answer. In next video, same circuit is implemented on breadboard and we have to find Vth, Rth and IL. Also, I will tell you applications of Thevenin theorem and how these calculations are useful for maximum power transfer from source to load. Thanks for listening this video lecture. Don't forget to subscribe my channel. Your suggestions and comments are very helpful for my next video.